Hello, welcome to this video looking at general relativity for the advanced higher physics course, and in particular looking at some of the consequences for general relativity and some of the ways that we know that it is true. So these are the things that we've talked about in the other videos in terms of what space-time is and that mass curve space-time, which is what general relativity talks about. The geodesic path and the world line space-time diagrams. We also talked about the equivalence principle, which states that gravity is equivalent to acceleration. So let's look at some of the potential impacts upon this. So here we've got a diagram from the Scholar resources showing that if we have a rocket moving upwards and we're looking at a beam of light going across the rocket, then we can see that because the rocket is going upwards, then the beam of light is going to take some time to go through the rocket, so it's not going to go out at the same height as it entered. And therefore, it's going to look a bit like picture B, where we've got a curved part of the light. And so this is one of the implications from acceleration. And because of the equivalence principle, if that is true for acceleration, then light can also follow a curved path when we're looking at gravitation. Okay, so this is explaining our beam of light sent across the spaceship accelerating upwards. The observer watching the spaceship from the ground, the light moves in a straight line. However, the spaceship will move slightly upwards in the time that it takes. So therefore it's going to strike a point lower on the wall than if the spaceship did not move. And so to this observer, it's going to appear that the light is bending and following that curved path that we saw. Okay, the equivalence principle said that if acceleration bends light, then gravitational fields are also going to bend light. And we call this effect gravitational lensing. So here's a diagram that might show us what gravitational lensing is actually doing. So the actual star could be positioned behind another star, let's say our sun, but it appears to us as if it is coming from that straight line because we're not aware that the large mass object like the sun is going to bend the light. What do we actually see? Well, when we're looking at images from the Hubble Space Telescope, we can see these rings around. So you can see rings of light around the center of the stars in circles. And this is the gravitational lensing that we're happening. So instead of coming from a point, it's bending all the way around the mass that's behind it, and we see these rings. In the class, you can kind of model this a bit. If you cut the bottom off a wine glass goblet, if you cut that off and then you put that over a dot, you would see this kind of ring effect. So it's acting as a bit like a lens, but it's a gravitational lens. So we explain this because the equivalence principle says acceleration and gravity are both going to bend the light. And so this has an impact on where we think stars or galaxies are when they're actually behind other stars or galaxies. So they appear in their apparent positions. Okay, so here's another diagram showing that. So we might think that the light is in those apparent positions when actually it's in the position in the middle. But the space-time itself is bent, and so the light is following this bending of the space-time. So the light's still traveling in a space-time in a straight line. It's just the space-time itself that is curved because of the mass of the object. And so we see this ring around the particular parts. Okay, so this is the light all the way around the circle, and the star that we're looking at is behind the star in the middle, or it could be a galaxy as well that do this. Okay, and this is known as an Einstein ring because of that. So one more consideration, if we've got a spaceship accelerating upwards and we've got light that is pulsed from the bottom to the top, by the time it reaches the observer at the top, the spaceship will have moved slightly upwards, and so it's going to take slightly longer to do that. And so if you have this weird clock that works by these pulses of light, then it's actually going to take slightly longer to reach the observer at the top than it does at the bottom. So one of the consequences of this is that the clock at the bottom of the spaceship is going to run more slowly than a clock at the top. Okay, and because of the equivalence principle, the clock in a gravitational field is going to run more slowly than in the absence of a gravitational field. So we can accelerate a clock in a centrifuge, spinning it round and round and round, and it will have a smaller time than the stationary clock. We can have the clock closer to the surface of the Earth. It will have a higher gravitational field there. If it's further away from the surface of the Earth, then the time will be greater. So the lower, the slower is the kind of way to remember that. So here's a summary. The greater the gravitational field strength, the greater the stretching of the space-time, so the clock is going to tick slower. So clocks on the surface of the Earth will run slower than a clock on Everest or a clock in a satellite. So GPS satellites need to be adjusted to take into the accounts of general relativity. They need to be slowed by 47 microseconds per day. They also need to be adjusted for special relativity because they are moving, and that needs to be taken into account. In extreme gravitational fields, clocks will run noticeably slower. The most extreme fields are black holes, and we've seen from certain films that the time appears to run slower as you get closer to that. And that is what scientists would predict is true, and Einstein predicts through his theory of general relativity. So the gravity or the curvature of space-time is so great in a black hole that time stops at this point we call the event horizon. More on that later in the course. Okay, so here's another diagram just showing compared to a clock on the top floor, the clock on the ground floor has a greater gravitational field strength, so it will tick slightly slower. Of course, you need a very, very precise clock to be able to see the differences. Okay, and that's because the curvature of space-time is greater, and that's what is having the effect on the ticking of the clock. Okay, Einstein produced his theory. Things were far removed from everyday experience and very difficult to test, but now through GPS satellites we can actually see that this is correct, and we have to build in these corrections according to Einstein's theories. Okay, and here's our summary, just saying again that the gravitational field is weaker at altitude, so it's going to be slower at altitude, faster at altitude than it is on the ground. So we need to take this into account. Without making these corrections, we get a difference of about 10 kilometers per day for our GPS mapping. So there's gravitational time dilation. In a non-inertial frame of reference, accelerating time is dilated, makes it longer. Time will pass faster in a smaller acceleration or gravitational field, and time will pass slower in a bigger acceleration or gravitational field. So satellites in orbit have to be fitted with a quantum clock that runs the same as on Earth, and we have to correct that time to be correct. So one of the other considerations we can see that there would be something called gravitational redshift. So again, the equivalence principle means that acceleration is similar to gravity. So if we've got a source of light at the top of the spaceship, the Doppler effect will mean that the observer at the bottom of the spaceship will observe a higher frequency than the source that has been emitted. So this is called gravitational redshift, because it's shifting towards the red end of the spectrum, the lower frequency end, where it's going to have weaker gravity or less acceleration, depending on which point of view that you're looking at. So this diagram sort of summarizing what that might happen to be looking like. Okay, so if a photon moves towards Earth, the photon's energy increases as it travels to a position of smaller gravitational potential energy. Therefore, the frequency ought to increase. So, gravitational redshift, we've got a wave coming from a source that's in a gravitational field, is reduced in frequency when observed in a region of weaker gravitational field. So if it goes from stronger to weaker, we get a decrease in frequency, which will be a redshift. If it's going weaker to stronger, then we would get an increase in frequency. That's what's showing in the diagram here. So the sun has a greater gravitational field. That's why it's got the blue end and the red end at the earth end, because it's got a smaller gravitational field. Einstein's theory of general relativity predicted gravitational waves, little ripples across space-time produced by massive accelerating bodies such as black holes orbiting each other, and we have now detected these in the LIGO, the Laser Interferometer Gravitational Wave Observatory, where basically we have two long tubes that look at light, and we look at accurately measuring the distance of one dimension and then accurately measuring the distance of another dimension, and we look at the tiny stretches and squashes. So they have to remove all tiny vibrations, and they're looking at details that are less than the width of subatomic particles for the changes. So we've now know that gravitational waves do exist, and we've now detected them. One final problem that general relativity predicted was what's called the precession of Mercury. So Newton's laws of gravitation were unable to predict the precise orbits of Mercury. So Mercury follows this kind of orbit that is shown here, and it didn't behave properly according to Newton's equations. So as it orbits the Sun, it follows an ellipse approximately, and it's found that the closest point of approach is not always the same place. It moves around the Sun. This is called a precession. And we could see that from the Earth, and we could predict where it was. People knew, and they could measure what it was there. Newton predicted it to 5,557 seconds of an arc, but that was slightly out from where it was actually. And Einstein was able to predict without any adjustments whatsoever that this should happen. So this proved that the general theory of relativity was correct. Finally, if we consider black holes distort space-time so much that the laws of physics break down at their event horizon. So there's a thought that they can create holes in the fabric of space-time itself. And some scientists talk about the many worlds possibilities with future and present linked between the two. So it could be a way of traveling to other places in the universe, but we honestly don't know. We will do more on black holes and more on their event horizon and what all that means later on. If you're interested in the topic, there are some good books here that you could read about. And finally, these are the things that you need to understand about special relativity, that it deals with inertial reference frames, and that general relativity, the subject of advanced higher, deals with non-inertial reference frames, and understand the equivalence principle, that it's not possible to distinguish between the effects on an observer of a uniform gravitational field and a constant acceleration. And this presentation has all been about the consequences of that.